Okay, so today we will just do 7C.3. So hopefully we've sort of made our way through some of C1, C2, but just 7C3, and then it'll be an opportunity to catch up over the weekend, make sure we're all ready to do 7D come back Monday. So all we're doing here, we're not learning a new skill as such, we're just applying it in a new context. And that's what we call a fair game. So we know from a probability distribution, right, you can calculate what we call the expected value, E of X, which is the mean, all right? And what this means is that if you were to repeat this experiment over and over and over again, this is the average result that you can expect, okay? That's what E of X is. And so we have a game here that involves, a simple game costs $1 to play, all right? So you have to show you can pay $1 to play it. It involves flipping a coin and guessing which side it lands on. If you guess correctly, you win $2. If not, nothing. Okay? So let's consider the possible events. You could win $0, and the probability of you guessing it correctly, we're going to assume it's half, okay, of flipping the coin, 0.5. Or you could win $2, and the probability of guessing that correctly, 0.5. All right, so let's calculate the expected value here. E of X is equal to the sum of, I'll write this out again, xi times pi. So this is from exercise 7C.2, and that's going to be each event multiplied by its probability added together. So we have 0 times 0.5 plus 2 times 0.5. Okay, so this is going to equal 0 plus 1, it equals 1. So the expected value is 1. And the cost to play is $1 as well. All right? So you're paying $1 to play this game, and on average, you're going to win $1. So you go down $1, and then you receive back $1. How much are you gaining each time you play this game? Zero. You're losing $1, all right, to play the game. You're putting the $1 in to play it, and then you're on average receiving $1 back. So this is what we call a fair game, and it is a fair game because the expected value of the distribution is equal to the cost to play. All right? A game is fair if the expected value of the distribution is equal to the cost to play. So let's answer this question. Determine if the game is fair. Yes, it's fair. E of X equals cost to play. That's why it's fair, because the expected value is equal to the cost to play. Would this be a good fundraiser? Well, the answer is no, okay? Because the person playing the game is not gaining anything, and the person who's running the game, who wants to raise money, they're not gaining anything either. No, not a good fundraiser, and that'll probably become clear in our next example as to why. I'll try and write messy, hey? All right, I'm just going to clear that example off. That's a nice, easy example introducing you to the idea of a fair game. Let's look at the next one, which is a bit more complex. Unless there's any questions about that. Very good. So we have a game costs $5 to play using a standard shuffled deck of cards. If you draw a face or an ace, you win $10. If you draw a 6 to 10 inclusive, you win $2. And if you draw a 2 to 5 inclusive, you win $1. Okay? So let's consider the possible events. I'm going to get this same table here. The lowest amount that you're going to win is $1. And that's if you draw a 2, a 3, a 4, or a 5. 2, 3, 4, or 5. And so the probability of that occurring then is 4 out of how many possible arrangements do we have? We have ace through 10, jack, queen, king, 13. 4 out of 13. Okay? So probability of getting a 2 to 5, 4 out of 13. Or if you get a 6 to 10, So a 6, a 7, an 8, a 9, or a 10. All right, there's 5 possible ways that can occur. Out of 13, you win $2. And then the big jackpot, the ultimate prize, $10 if you draw a face or an ace. A face means a jack, queen, or king, or an ace. Okay, 4 out of 13. And you can solve that by elimination because you know all of the probabilities have to add up to 1 anyway. Okay, so we've got the probability distribution here. All right. To test if the game is fair, we say, does E of X equal the cost to play? So the cost to play here is $5. Let's calculate E of X. So each event multiplied by the probability of that event, added together. On 13. So it's just over 4. 4.05? 4.15. Okay, so what this means is each time you play this game, on average, you would expect to win $4.15. All right? So if you were to play the game 100 times, you would win $4.15 times 100, $415 on average. That's what we expect. Okay, now the cost to play is $5. So each time you play this game, it costs you, you're investing $5. So what is your expected gain or loss? How much are you winning or losing each time you play the game? $5 to play it. Okay, so you're losing $5 there, but then you get back, on average, $4.15. What's the average gain or loss? Loss of 85 cents. Very good. We can see you're only getting back $4.15, which means you're losing 85 cents on average. So let's address the way of the chance. Draw a probability distribution. Good. Determine if the game is fair. No, not a fair game. Because E of X does not equal cost to play. E of X is less than the cost to play. And this is going to be a good idea for a fundraiser because each time the game is played, the person who's running the game is winning 85 cents. Every time they play the game, they're winning on average 85 cents because they're getting $5 from the people who are coming to play it, and then they're only giving back $4.15. So they're keeping on average 85 cents. If they play this game 100 times, all right, they can expect to have got, what's that, 85 bucks. All right. So that is 7C.3, fair games. All we're doing is calculating E of X, comparing it to the cost of play. They start pretty easy, but they will get a bit more complex. So let's start with that.